Hello everyone. Today in this video of piezoelectric material, we will solve another related to the piezoelectric material in the course of in the course of smart materials. So this is problem number 4.17. So what is the problem? So a piezoelectric extender operating in the 1-3 mode has the cross-section geometry shown in the figure 4.42. This is our geometry. This is APC 856 piezoelectric materials, and this is the brass. We use brass as a substrate in the 1-3 mode. So this is the thickness direction, right? Because we are applying the voltage in the thickness direction, this direction, this is the thickness direction, right? And we are applying the force in another direction. So let's see in the figure 4.42, compute the strain in the one direction. Why one direction? Because we are applying the electric field in three direction, and this uh, operating mode is 1-3 direction, right? For an applied field, electric field is 0.75 m volt upon meter. Assume that the brass at the modulus 117 GPa and the piezoelectric material is APC 856. So this is the program of extension mode of the 1-3 mode. We already discussed the 3-3 mode, right? So this is the 3-1 mode or 1-3 mode. If we apply the if we apply the force in the one direction, or in the 1-3 mode, or in the 1-3 plane, then the mode is 1-3 mode, because we are applying force in only one direction. If we apply the force in three direction, then the operating mode of the piezoelectric material or sensor or actuator is 3-3 mode, right? So how to solve this problem? uh, in previous videos we already discussed about 3-3 mode. Then strain in 3-3 mode is strain in 3-3 mode S3 is uh, D multiplied by A, piezoelectric strain coefficient and the electric field, right? uh, and this term will get 0 because we are not applying any force. So stress is 0, right? Stress in the material is 0 because we are only applying the electric field. So S3 will comes out to be DE, where D is the piezoelectric strain coefficient and the E is electric field. But this problem is not the 3-3 operating mode. This is the program of 1-3 operating mode, right? And this is the extender. So like this. So basically in this figure, what is the extender means? This is fixed, right? If we consider that this is fixed and we applied the electric field in this and this piezoelectric material, then this will vibrate like this, right? This will like this will go like this, and when we reverse the current, this will go like this, right? So this will behave like this, right? So this will actuate, actually this will actuate like this. So we have to compute the strain in the one direction, right? In one direction, this is the one direction. So we have to compute the strain in one direction due to the electric field applied in this direction, 3 direction, right? So let's see. So you can also see that this is not the tension, this is the case of compression. When uh, this will vibrate like this. If the direction of electric field is like this will vibrate like this. And again, if we reverse the direction, this will bend like this. Like this is the bending case, actually extension bending case of 3-1 mode piezoelectric material. So let's see the solution. This is the property table for the APC 856. These are the engineering constant related to the APC 856. So what we have to given, E3 is given. E3, that is the electric field in the three direction or thickness direction, which is the 0.75 megavolt per meter. Young's modulus of brass is given because we are using substrate as a brass. This is piezoelectric material. This and this upper layer is piezoelectric material of 1 mm and 1 mm. So total thickness of the piezoelectric material is 2. Total thickness of brass is also 2. So brass is a substrate and this is a piezoelectric material, right? So Young's modulus of brass is given, which is 117 GPa, and material is APC 856, which is given here, which is given in the property table, right? And from the image we can find that the thickness of substrate is brass, which is 2 mm, and the thickness of piezoelectric material is also 2 mm, because this is our piezoelectric material, this, and this is our piezoelectric material. Then total thickness is 1 plus 1 is 2 mm, and this is our substrate. Then the thickness of the substrate is also 2 mm, right? So so these are the two thickness. So the formula or the relation between the strain and the D3 and electric field is given by this formula. The derivation of this formula is not given in the question, but if you see the 3-1 extension mode, right? This is the program of 3-1 extension mode. So you can easily get this formula from 3-1 extension mode of piezoelectric materials, uh, from the book of engineering analysis of smart materials and systems. So this is the relation is given for the extension 3-1 mode, right? So what is psi e is nothing but this is the ratio of ys upon y1 etp, where y1 is the Young's modulus in the one direction when the electric displacement is 0, right? Y1 means when the electric displacement is 0, then y1 is given here from the table. This is the electric compliance, so this is S1. So electric compliance is nothing but the reciprocal or 1 by y, right? So uh, compliance, we denote the compliance by the small s, which is nothing but 1 upon y, right? So you can find y here from this value, right? From this value 15 multiply by this value, so you can find easily y from here, right? From the table. And d13, this value is also you can find from here, right? So let's see. So this will become, when we put all the values, ys means subtract is brass, and the brass properties are given here, and this is brass thickness, which is 2 mm. So when we put all the values in this psi formula, this will comes out to be 1.755, right? Because this is a ratio, so this will not have any unit. This all the units will cancel out each other, right? So when we put all the values in this strain formula, because D13 is the piezoelectric strain coefficient, which is given in the table as I shown earlier, and the E3 is electric field, which is this value, right? 0.75 megavolt per meter is our electric field in the three direction, right? In the thickness direction. Like this is a piezoelectric extension mode. This is the direction 1, right? This is the direction 2, and this is the thickness direction, which is the z direction actually, right? So when we put this value and this value, we get this, right? This is the our D3 value, which is in minus. This is E3 value, and this is psi E value, which we have computed here, right? 1.755. So this will comes out to be 70.78 microstan, right? This will comes out to be 70.78 microstan. This is minus because, as I discussed earlier, that this material will, this is fixed, right? Here, like suppose here this is fixed, and this will vibrate like this because we use this combination of this composite. Like we form this composite for the actuation mode, so this will actuate like this, right? When the electric field is in upper direction, like this direction, so this will actuate like this. When the electric field is in this direction, this will actuate like this. And if you have the circuit in which the electric field is changing with respect to time, like sinusoidal or any other electric circuit in which the electric field direction is changing, but changing with respect to time, then it will vibrate like this, right? And the frequency of this vibration is depend on the frequency of the changing of the electric field, right? So this is the complete solution of this problem. If you have any doubt, please post on the comment section, and if you have similar and another problem, you can send the problem on our email, which is given in the description of this problem, right? Thank you for watching this video. Thank you.